What's up, Algebra Bros and Broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear. Hey, welcome. Today we're going to take a look at diagonalization, which is a very interesting topic for the course, and I think you're really going to enjoy it. Let's go ahead and talk a bit about it. A square matrix A is said to be diagonalizable if A, that should be if, we'll fix the typos while we're here. A square matrix A is said to be diagonalizable if A is similar to a diagonal matrix. That is, if A is equal to P times D times P inverse for some invertible matrix P and some diagonal matrix D. So it's that similarity relationship again. We're saying I can write my matrix A as similar to some diagonal matrix D with this invertible matrix P. And then that means the matrix is diagonalizable. So let's go ahead and talk about a diagonalization theorem. It says an n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. So this is important. If I have a square matrix, an n by n square matrix, I need exactly n linearly independent eigenvectors. If I don't have enough eigenvectors, I won't be able to diagonalize. So if I have a 4 by 4 matrix, I need 4 linearly independent eigenvectors. If I have a 7 by 7 matrix, I need 7 linearly independent eigenvectors, so on and so forth, in order to diagonalize. We go on, we say, in fact, A is equal to P times D times P inverse, with D a diagonal matrix, if and only if the columns of matrix P are n linearly independent eigenvectors of A. In this case, the diagonal entries of matrix D are eigenvalues of matrix A that correspond respectively to the eigenvectors in P. So what we're saying is we're going to build this matrix P by taking its columns as eigenvectors, and we're going to build the diagonal entries of the diagonal matrix D by using eigenvalues as the diagonal entries, but those diagonal entries have to correspond to the respective eigenvectors in P. So we have a bit of freedom as to how we can select one of these, but as soon as we select either diagonal entries of D or the columns of P, it then tells us how we should write the other matrix and vice versa. And we'll talk about how we do that. We'll do tons of examples. I'll explain it. I'll wave my hands around, all sorts of stuff. In other words, A is diagonalizable if and only if there are enough eigenvectors to form a basis of Rn. Here we mean a complete basis. In order to form a complete basis of Rn, and we call such a basis an eigenvector basis of Rn. We're going to talk a bit first about working with diagonal matrices, what it means to have a diagonal matrix. A diagonal matrix is a matrix where I only have entries on the main diagonal. And I'm not going to, I guess I could sort of draw one in general, but I'll just give you a 3 by 3 example. And then I would need zeros everywhere else is a diagonal matrix, right? And those values can look however they look, but this would be a 3 by 3 example of how a diagonal matrix would appear. Right? I only have entries on the main diagonal that could be non-zero. Everything else has to be 0. For example, here I have a 2 by 2 diagonal matrix. On the main diagonal, I have a couple non-zero entries, but everything else has to be 0. So we say let A be equal to PDP inverse, and I want to compute A to the power of 4, and I'm given matrix P, I'm given diagonal matrix D. Now, there's a comment that I think is worth sort of exploring first, is computing A to the 4th. Now, there's a couple ways I could do this, right? I could find P inverse, and I could multiply P times D times P inverse, and that would give me matrix A. From that, I could then compute A times A times A times A to find A to the 4th. But that's not what we want to do. That's not going to be the best way to go about it. So let's go ahead and talk about what is the best way to go about it. Think of it this way. A to the power of 4 is going to be A times A times A times A. And since A is equal to P times D times P inverse, let's make that substitution here. So we're just talking about this sort of in general. We're getting sort of a bit of an abstract idea here. So A is P times D times P inverse times P times D times P inverse times P times D times P inverse times again P times D times P inverse. All right, and that's how A to the fourth looks. But I want you to notice something very important here, is that when I'm multiplying these together, I have P inverse times P right next to each other. And wherever I have this P inverse times P, that's going to give me the identity. So then what do I wind up with? I'm sure you probably can get a sense already. I end up with P times D times the identity. Multiplying by the identity is a multiplicative identity for matrices. So I'll skip over that, right? And then times D times the identity, which again, we'll skip over that, times D times the identity, and then times D, and then times P inverse. And really, if I was writing this out a bit more carefully, I would show that I'm multiplying by the identity. I have that sort of, I've noted it here, but then multiplying by the identity would sort of go away in that next step, leading me right here. And I can write this shorthand, right? The goal isn't maybe to leave it written out like this, but I can write this as P times, here I could say, well, this here is D to the power of 4 times P inverse. So this is a very interesting result. Since A can be written as similar to a diagonal matrix, computing powers on this matrix A to the fourth is equal to P times D to the fourth times P inverse. So that's a very useful result. I want you to sort of think about that, right? We're saying since A is equal to PDP inverse, A to the fourth is P times D to the fourth times P inverse. So that's going to be very helpful. Now, there's another comment that we can make about powers on a diagonal matrix. I think you're going to see what's going to happen, but let's sort of explore this together. It'll be sort of a bit of a discovery. This was diagonal matrix. I believe it looked like this, right? Yeah, diagonal matrix D. And you know, if you can tell what's happening, go ahead and type it down in the comments. Let me know what you're thinking. But let's go ahead and just sort of explore it organically. Let's do D squared is D times D, which means I would multiply this matrix to itself. So I'll write it out. And we'll use our row column rule to multiply. So first row, first column, 2 times 2 plus 0 times 0 gives me 4. And then sticking in that first row, but now moving to the second column, 2 times 0 plus 0 times 1 gives me 0. Down to the second row of this the left matrix, and then back to the first column of the second matrix, the right matrix. 0 times 2 plus 1 times 0 gives me 0. And then bottom row, last column, 0 times 0 plus 1 times 1 gives me 1. So that's how D squared looks. If I want D cubed, we could think of this like D times D squared. So we'll just take matrix D and we'll multiply that to what we have for D squared. And again, we'll work with our row column rule. So first row, first column, 2 times 4 plus 0 times 0 gives me 8. 2 times 0 plus 0 times 1 gives me 0. Moving down to the second row, back to the first column, 0 times 4 plus 1 times 0 gives me 0. Bottom row, last column, 0 times 0 plus 1 times 1 gives me 1. And last for us to compute for this example, D to the fourth, which we can write as D times D cubed. So take matrix D, and then times D cubed I just found here. Maybe you're already getting an idea as to what this phenomena is, but let's take a look at this. So first row, first column, 2 times 8 plus 0 times 0, it's a 0 there, it's going to give me 16. 2 times 0 plus 0 times 1 gives me 0. Second row, first column, 0 times 8 plus 1 times 0 gives me 0. And then lastly, 0 times 0 plus 1 times 1 gives me 1. So this is what I get for D to the fourth. Let's go ahead and sort of showcase this a bit better. We found D to the fourth was 16, 0, 0, 1. And it isn't just by happenstance, right? We're noticing as we're computing it, what's happening is it stays a diagonal matrix first and foremost, but I'm really just raising those entries to that power, right? Here I have 2 to the 4th gives me 16, and 1 to the 4th gives me 1. So really nice. I wouldn't necessarily say to compute this in the way that we did, though you can. It's not the end of the world either. But you would want to think about this as a property, using this as a shortcut. Using this as a shortcut. And then what we had, matrix P, was given. Let me write that one back down again. That had rows 5, 7, 2, 3. And I want to find P's inverse. So we didn't do this yet, but let's find P's inverse. So that's 1 over the determinant of P, so multiplying the main diagonal, 5 times 3 is 15, minus 7 times 2 is 14. And then since it's a 2 by 2, we know we can go to the entries on the main diagonal and swap them. So 5 and 3 switch where they are. And then off the main diagonal, we just flip the sign. So 7 stays where it is but becomes negative 7. 2 stays where it is but becomes negative 2. And I'll point out here that 15 minus 14 is 1. So my coefficient is 1 over 1. So we have that P inverse. I'm not really doing much in the lines of scaling, but P inverse is this matrix right here. And now we can actually finish the question. So it says find a to the 4th. We know that that's P times d to the 4th times P inverse. And I actually have all of these pieces. So say first is matrix P, and then is the matrix d to the 4th, and is matrix P inverse. And we can fill these in. Matrix P had rows 5, 7, 2, 3. Remember, d to the 4th was 16, 0, 0, 1. And then P inverse, we just found the inverse, right? That had rows 3, negative 7, negative 2, 5. Now I want to compute this. Now something very important for multiplying this out, I have to go from left to right. I have to go from left to right. So here I'm going to start with P times d to the 4th. And I want to do my row column rule to compute this. So say, okay, here I have 5 times 16 plus 7 times 0. So it's really 5 times 16. And I like to think about this sort of like distributing. So I'm going to get 50 plus 30 is going to give me 80. And then finishing off this top row, 5 times 0 plus 7 times 1 gives me 7. Move down through the second row back to the first column. 2 times 16 plus 3 times 0 gives me 32 plus 0, or 32. And then very last, 2 times 0 plus 3 times 1 gives me 3. But I still have to multiply, and it's still on this right side. I still have to multiply by P inverse. So just a bit more to go with this. And we'll go ahead and we'll use that row column rule again. So here, first row, first column, I'm going to have 80 times 3 plus 7 times negative 2. 80 times 3 is going to give me 240. And then 7 times negative 2 is going to give me minus 14. So I'll just write it this way for now and then finish it up in the next step. Staying in that first row, but now to that second column, I get 80 times negative 7 gives me negative 560 plus 7 times 5, which is plus 35. And then now to the second row, first column, 32 times 3, we'll think, okay, that's going to give me 96. And then plus 3 times negative 2 is minus 6. And then second row, second column, 32 times negative 7. And again, I like to think of this like distributing, right? If I bring a negative 7 into a 30 gives me negative 210, and then negative 7 into 2 gives me negative 14. So that's going to give me my negative 7 times 32, and then plus 3 times 5, so plus 15. So kind of a weird way to do arithmetic, but if you have a healthy fear of arithmetic like I do, I think this is the best way to do it mentally. And then now we would just go ahead and finish the arithmetic. So I'll say, okay, 240 minus 14. So that's going to give me 226. I have negative 560 plus 35. So that's going to give me negative 525. 96 minus 6 is going to give me 90. And then here, I like to go maybe to the end of this. Negative 14 plus 15 gives me 1. Negative 210 plus 1 gives me negative 209. And this, although it took us a bit of work, is going to be the better way to compute a to the power of 4 using the fact that we have this relationship with diagonal matrices. So that's what we're going to want to do for computing this. We can use some of these ideas that we've built to help with this next question. I want to use the fact that A is equal to P times D times P inverse. And here I'm actually given this written out. Matrix A is equal to P times D times P inverse to compute A to the power of K for any arbitrary positive integer K given this relationship. Now, what we said before is still going to be true, so I can generalize this and say A to the power of K is equal to P times D to the K times P inverse. And I already have P and P inverse. The only thing I have to find is D to the K. And we actually have a nice shortcut for that. D is this sort of generic looking diagonal matrix. On the main diagonal, I have entries A and B. But then, since it's a diagonal matrix, the rest of those entries have to be zeros. And we'll say if we remember what happened in the previous example, D to the power of K, well, that means I'm going to be raising these diagonal entries to the power of K. So A to the K and B to the K on the main diagonal. But this is preserved that it's a diagonal matrix, so everything else is still a 0. And now, since I'm given the rest of the pieces, I can compute A to the K directly. A to the power of K, it's going to be matrix P, which I can look up above to see it, has rows 1, 0, 2, 1. Times D to the K, which I just computed that. Didn't really have to do too much work for that. And then times P inverse, and I can look up there to see what that's supposed to be. Rows 1, 0, negative 2, 1. And then remember, it's important that we multiply this in the correct order. I have to go from left to right. So I want to start with P times D to the K. And we'll do our row column rule with this. So first row, first column, 1 times A to the K plus 0 times 0 gives me A to the power of K. Sticking in this first row, but now moving to the second column, 1 times 0 plus 0 times B to the K gives me 0. We'll go to the second row, back to the first column though. 2 times A to the K plus 1 times 0 gives me 2A to the K. And second row, second column, 2 times 0 plus 1 times B to the K gives me B to the K. And then I still have to multiply this by P inverse. But we should be able to do this last bit of multiplication and should be good to go. Should be good to go. Let's see what this does. So first row, first column, A to the K times 1 plus 0 times negative 2 gives me A to the K back. First row, second column, A to the K times 0 plus 0 times 1 gives me 0. We'll go to the second row, back to the first column, 2A to the K times 1 plus B to the K times negative 2. We could say, well, okay, 2A to the K times 1 is 2A to the K. And then negative 2 times B to the K gives me a minus 2B to the K, all for this entry. And then we're going to do second row, second column. So 2A to the K times 0 plus B to the K times 1 just gives me B to the K. And this looks good. If I want to leave this as my representation for A to the K, that's fine. But there's maybe a nicer way that I could even try to write this depending on what you want it to look like. But I'm going to say A to the K and 0 look good. But this entry right here, we could factor a 2 out, right? I could say that's 2 times in parentheses A to the K minus B to the K. That I think looks nice, right? And then that last entry is still just B to the K. And what's nice about this is if I have the specific form, this is a very specific example, I'll give you that. But now if I want to specify what that positive integer K is, and if I know what A and B are, then I could figure out what this a to the power of k would look like just by dropping those values in. So I've got this very nice general formula if this were something that I was trying to do. Let's take a look at this next question. We're going to sort of revisit one of the theorems at the beginning. But it says, use the diagonalization theorem to find the eigenvalues of A and a basis for the eigenspace. And remember that we're still talking about the similarity relationship that A is equal to P times D times P inverse. And I can see that D is this diagonal matrix right here. And then here I have matrix P. Here I have the inverse of that matrix P at the very end. And I'm really starting from this matrix A. But let's go back and read what we had read earlier about this, because that's going to be very relevant now. Right here. In fact, A is equal to P times D times P inverse, with D a diagonal matrix, if and only if the columns of P are n linearly independent eigenvectors of A, and in this case, the diagonal entries of matrix D are eigenvalues of A that correspond respectively to the eigenvectors in P. And this is what we're trying to illustrate in this example. It's actually a fast example. We're going to be sort of exploring this a bit more in depth later on. But if I go to this diagonal matrix D, the diagonal entries should be my eigenvalues. My eigenvalues are 3, 2, and 3. So that's worth mentioning. So I can say from matrix D, the eigenvalues are lambda equals 3. And this actually happens twice. So we'll say lambda equals 3, multiplicity 2, and lambda equals 2. And this is multiplicity 1. Just happens once over. But important also to notice that in this matrix P are the eigenvectors. So matrix P has columns that are, I'll be very colloquial here, that are my eigenvectors. Right? They're yours, ours, we're sharing them, right? But matrix P, those columns of matrix P, those are the eigenvectors that we're looking for. But they correspond is important. Let me try to color code this. So when I say, okay, 3 is an eigenvalue, this particular eigenvalue 3 corresponds to this first column. It's that diagonal entry in the first column of D, right there, refers to this first column vector of P. But I have another, so this happens to have that repeated eigenvalue. And it is kind of arbitrary to say which is which, because really this eigenvalue, we only work with it once and it generates 2 eigenvectors in this case. But here, this very last column of D, the diagonal entry that has the eigenvalue, corresponds to this third column of P as the eigenvector. And there might not always be some repeated value, right? So maybe a good idea to color code it differently. But these 2 are the same eigenvalue, and it gives me 2 eigenvectors. And then we could say right in the middle, this middle column of diagonal matrix D, its diagonal entry 2 is an eigenvalue that corresponds with this eigenvector, that middle column of P. So I can actually tell you the relationships, right? These are respective. They're not all mix and matched crazily. So I could say, okay, so I don't got a lot of room for this, but let's do it. Lambda equals 2 has eigenvector, we'll abbreviate that. That eigenvector that corresponds to lambda equals 2, remember that was in the middle, is -1, 1, -1. And then we had lambda equals 3 has eigenvectors. And if I want to make these into sets, if I'm trying about building a basis for an eigenspace, and this is going to be, because lambda equals 3 had 2 eigenvectors. Yes. And what were those eigenvectors? It was 1, -1, 0. was one of them, corresponding to the eigenvalue of 3. But then also in the last column, corresponding to the eigenvalue of 3, 0, -1, +1. So this is just about dissecting the results, right? So find a basis for the eigenspaces. So this would be, right here would be a basis for the eigenspace corresponding to lambda equals 2. And then here this, of course, this set with the two vectors would be a basis for the eigenspace corresponding to lambda equals 3. I have some helpful steps down here which I want to talk about next, because we're going to be doing this together. So we're not likely going to be given the similarity relationship between A and the diagonal matrix D. We're going to be diagonalizing. How do we diagonalize? Well, I have some helpful steps here. I do hope they help you. We'll be doing examples. Steps to diagonalize an n by n matrix A. First, find the eigenvalues of matrix A. Then, find n linearly independent eigenvectors of A. Steps 3 and 4 really sort of go hand in hand. Construct matrix P from the vectors in step 2. Construct diagonal matrix D from the corresponding eigenvalues. And be really careful when you do this. Make sure things stay respective. Let's see a first example together. Diagonalize the given matrix A. Now we know how to find eigenvalues and how to build eigenvectors from that. So a lot of this is going to be familiar work to the previous sections. If I build A minus lambda I, really, truthfully, we're just subtracting lambda away from the entries on the main diagonal. So instead of 1, I'm going to have 1 minus lambda, and then 0, and then 6. But instead of -1, I'm going to have -1 minus lambda. And now I want the determinant of this. I want the determinant of A minus lambda I. And we multiply on the main diagonal, which is 1 minus lambda times -1 minus lambda, and then minus, we subtract away the product on the off diagonal. 0 times 6 gives me 0. And then we set that determinant equal to 0 to try to find the eigenvalues. And subtracting 0 away, I can just get rid of this. There's a bit of a shortcut to this, which I'll talk about in a second. But leaves me with 1 minus lambda times -1 minus lambda equals 0. And we can actually pick the eigenvalues right off of this. I wouldn't want to expand this out because I can just use the factors. Either 1 minus lambda is equal to 0, which means lambda is 1, or -1 minus lambda is 0, which means lambda equals -1. Now, of course, the shortcut is noticing that this is a triangular matrix, so the eigenvalues are actually right there on the main diagonal. So good practice working with the characteristic polynomial and setting it equal to 0. Now that I have the two eigenvalues, I want to work with them one at a time to build my eigenvectors. And, however, the order doesn't matter. I like to start with, if I have a positive 1, I like to start with a positive 1. I would like to start with whatever has the largest value, typically. No reason why. Let's do lambda equals 1 to start. And then if I go ahead and plug this in, I'm going to get 1 minus 1 is going to give me 0, and then 0. Now I want to augment this with the 0 vector, keeping that in mind. And then in the second row, I'm going to have 6. And then remember, I'm plugging 1 in for lambda. So -1 minus 1 gives me -2. And then I'm augmenting with that 0 vector. Now right away, we'll notice I have a row of all zeros. I should bring that to the bottom. And then aside from that, so we'll do a row interchange. Aside from that, I want to scale the top row, and I wouldn't scale to get fractions. The goal isn't necessarily to get a reduced row echelon form, though that's always good. The goal is just to build the vector. So I would say, let me do a 1/2 row 1, and that's going to give me 3, -1 augmented with 0, and I have my row of all zeros at the bottom. And this is good, right? I can build a vector from this. What is that equation telling me? says 3v1 minus v2 equals 0, or that 3v1 is equal to v2. And notice I'm just solving in sort of an algebraic sense, not really solving for the basic variable in terms of the free variable perfectly, just something to get a relationship. You could solve for v1 from here, right? And that would be perfectly fine. It's not going to give you probably a different result either. For my eigenvector, I'm going to go ahead and make a choice. I'm going to say, well, let v1 be 1. And then 3 times 1 gives me v2, which gives me 3. And like I was saying, if you solved for the basic variable v1, you'd probably say something like v1 is 1/3 v2. And then you would make probably the same choices. Try to get these to look as nice as possible. Can they stay as fractions? Yeah, of course. Do I want to do that? No. Make them look nice. If your eigenvectors don't look as nice as they possibly could, you're doing it wrong. Make the eigenvectors look beautiful. They have feelings too. So if you had a relationship like this, you'd probably say, well, if I want to clear the fractions, let v2 be 3, and then v1 is 1. So it really doesn't give me, there's no huge incentive to doing this. I like to write right by my eigenvector because they like to be together as pairs. I like to say the eigenvalue that presented this eigenvector. So I like to kind of bundle them together like that. If you want to give them little nicknames, call this little lambda sub 1. And this could be, well, I already said v1 and v2 are the unknowns here, so maybe I could call this little v sub 1, but it is a vector and not an entry, so I'm going to be sort of careful with my notation then. You could use a's and b's here, something like that maybe. You know what I'm talking about. Let me know if you don't. I'm happy to chat. Just trying to make sure that my notation is good. Let's pick that other eigenvalue, lambda equals -1, and we do it all over again. Plug in that value in for lambda. So 1 minus -1 is really 1 plus 1 gives me 2. And then 0, and then 6 was there. And then plugging -1 in, -1 minus -1 is -1 plus 1 gives me 0. And I can scale both of these rows, do 1/2 row 1, do 1/6 row 2. They're both going to look identical, 1, 0 augmented with 0. And I can eliminate row 2, replacing it with row 2 minus row 1. So we'll get a row of all zeros at the bottom. But I still have this row on top, 1, 0 augmented with 0. And now, what is this trying to tell me? It's telling me v1 equals 0. And nothing about v2. v2 is just equal to v2. It's my free variable, right? v2 is free. So when I go to pick the vector in this case, I know that first entry has to be 0. And I can choose whatever I want for the second entry. Remember though, eigenvectors have to be non-trivial. So don't pick 0. Don't give me the 0 vector. That's not going to work. That's not an eigenvector. It has to be a non-trivial vector. So we say, well, what is the next nicest value I could pick? Could you pick 11? Could you pick 239? Could you pick pi? Yes, but you are going to pick 1 because you respect yourself. You know it's the right move. You know it's the right thing to do. And this corresponds as an eigenvector to the eigenvalue lambda equals -1. And again, if you want to give these little nicknames and make sure the world knows it's a vector, then that's not a bad idea. Now we're actually ready to construct. So we have A is equal to P times D times P inverse. And really, when diagonalizing a matrix, the important thing are writing out the invertible matrix P and the diagonal matrix D. Let me actually write these in this manner, because I want to show you how we write these in a respective manner and how important it is. So I'm going to go in the order that I worked with it, but you could have done them in a different order, and this should still be fine. I have worked with lambda equals 1 and then lambda equals -1. So when I go to my diagonal matrix, I already know how it's going to look in general. I'm going to put that first eigenvalue in the first column as the diagonal entry, the second eigenvalue in the second column, as the diagonal entry. But and you could put these in the opposite diagonal entries. I could do -1 here, +1 here. But what matters, though, is that the eigenvectors building the columns of P have to correspond to these. So since I put in the first column of D for its diagonal entry eigenvalue 1, the eigenvector of eigenvalue 1 needs to be this first column. I can't put it over here. That would be wrong. These have to stay so they coincide correctly, so they map up nicely. So with lambda equals 1, I had vector 1, 3. So I'm designating it in this first column, 1, 3. And I have this little stray mark there that's going to bug me, so I have to erase it. But like I was saying, if your eigenvalue of 1 was here, that column would have to be here. They have to sort of follow each other. They want to sort of match up nicely. Then here in the second column of D in the diagonal entry, I have eigenvalue -1. Corresponding to that is the eigenvector 0, 1. That better be my column here in the second column. And this is really all I need to showcase to state that I've found the matrices that diagonalize matrix A. If you really want to, you can find P inverse. I'm not saying don't do that, but I'm saying it's really not the biggest part of this. P inverse in this case, I get 1 over, and then here if I find the determinant, 1 times 1 is 1, minus 0 times 3 is 0. Entries on the main diagonal, we swap them, but here it's not really going to seem too apparent that we've done that. Entries off the main diagonal, we flip their sign. 0 is neither negative nor positive, so it's just going to stay 0, and then flip the sign on the 3, of course. So P inverse, if I want to find it, is actually this matrix right here. So when we talk about diagonalizing a matrix, it's really these pieces that we're looking for. Should you check your work? You could. Do you always have to? Maybe not. But if you want, if you're asked to, if I ask you, check your work, there's a couple ways you could do this. You could find P inverse like we did, and check to make sure that A is equal to P times D times P inverse. However, there is a better, more efficient way to check, and I want to share that with you. If I go and multiply both sides on the right by matrix P, I want you to notice over here that P inverse times P is the identity. And what this tells me then is that A times P is equal to P times D times the identity, which is just P times D. So this is a equivalent statement that I can check. And since I said it's not necessarily always imperative to find P's inverse, it does exist and we can find it. If I find matrices P and D, those are sort of the important ones to find, I would say. And if I want to check my work, I can actually just check that A times P is equal to P times D. And let's actually do this check for this first example. A times P. What was matrix A? What is matrix P? Matrix A was all the way at the beginning. We diagonalized that matrix. That had rows 1, 0, 6, -1. And then matrix P, we just found that. Let me read these off by the columns, because the columns are the eigenvectors, 1, 3, 0, 1. Not to confuse anybody, but I'm excited about those columns. And we'll compute this, but then we'll also find P times D. So I'll get some room for that. Matrix P, I can see it, so I'll just rewrite it. And then D was my diagonal matrix, but I had to make sure that the eigenvalues matched up. So it was 1, 0, 0, -1. And let's do the computations here. A times P, let's use our row column rule just to check. So 1 times 1 plus 0 times 3 gives me 1. 1 times 0 plus 0 times 1 gives me 0. 6 times 1 plus -1 times 3, 6 minus 3 gives me 3. 6 times 0 plus -1 times 1 gives me -1. And let's see what we get if we do P times D. These should be the same. But let's see if we mess something up. 1 times 1 plus 0 times 0 gives me 1. 1 times 0 plus 0 times -1 gives me 0. 3 times 1 plus 1 times 0 gives me 3. Moment of truth. 3 times 0 plus 1 times -1 gives me -1. So these two are equal. They are the same. So we have, in fact, checked our work. And since we know that A times P is equal to P times D, This is an equivalent statement because if I multiply on the right by P inverse, P times P inverse gives me the identity. So I know then that A is equal to P times D times P inverse, and that these matrices P and D are the ones that do the diagonalizing. So successful. Hey, what are we here for? We want to take a look at another example. So let's go ahead and see another example of this. Got my cat Spumoni here. Do you want to see another example of diagonalizing? What do you think? What do you think, baby? Diagonalize that matrix. There we go. It's always good to have your help. Doing a great job. Keep up the good work. Diagonalize the matrix. You know what we got to do with this matrix. Let's find A minus lambda I. Remember, we've seen a lot of examples of this. I want to subtract lambda on the main diagonal. The rest of those entries stay the same. Let's find the determinant. Determinant of A minus lambda I. So we're going to have 2 minus lambda times 4 minus lambda minus -1 times 1, which is minus -1. And then set that equal to 0. Let's expand this out. Negative lambda times negative lambda gives me positive lambda squared. We have -4 lambda and then minus 2 lambda. And then 2 times 4 gives me 8. And then we have plus 1 equals 0. So this is going to give me lambda squared. We have minus 6 lambda plus 9 equals 0. And if you can factor it, you're going to want to factor it. You're going to want to factor it. This will factor beautifully. Multiplies to 9, adds to -6. It has to be lambda minus 3 and lambda minus 3, which means that I have eigenvalue lambda equals 3 with multiplicity 2. Or you could say lambda equals 3, lambda equals 3. Lambda equals 3 repeated. So I'm only going to work with it once. I don't want to work with an eigenvalue and then work with that same eigenvalue again because it isn't going to produce any different sort of arithmetic. But I am hoping that I can get 2 eigenvectors from this because I only have the one eigenvalue with multiplicity 2. So let's work with lambda equals 3. It's the only choice we have anyways. And hope for the best. So if I go ahead and plug this in, say, okay, 2 minus 3 gives me -1. Then -1, and then we add 1. And then 4 minus 3 gives me 1. Physically plugging that eigenvalue in. And we'll say, well, in this case, I could go ahead and do some row reduction. So here I could replace, for example, row 1 with row 1 plus row 2, and that's going to give me a row of all zeros. And row 2 is going to stay the same, and then I dislike how this looks, so I would do a row interchange. So 1, 1 augmented with 0 for row 1, and then 0, 0 augmented with 0 for row 2. And this is all we can do. So what is this telling me as an equation? It's saying v1 plus v2 equals 0, or that v2 is equal to -v1. And I can build a vector from this. I'll say, well, let's let v1 be 1, and then v2 is the opposite of that, so -1. And this is my vector corresponding to lambda equals 3. However, my other eigenvalue is the same eigenvalue. I'm not going to do this again because it's not going to produce a new linearly independent vector in this case. Right? It's not going to give me new information because it just gave me the information that it had. And this is a problem. Right? In order to diagonalize a 2 by 2 matrix, let me write it down. In order to diagonalize a 2 by 2 matrix A, I need 2 linearly independent eigenvectors of A. In this case, I only got one eigenvector. What does that mean? This means matrix A is not diagonalizable. So I cannot diagonalize this matrix. I don't have enough eigenvectors. So we only got the one eigenvector, and there wasn't another distinct eigenvalue to work with. It was this one repeated. So I'll make a little note up here. Not enough eigenvectors to diagonalize. Sad face. It's a bummer, right? We wanted to diagonalize, but we can't. We're not always able to do this. I need to make sure I have enough eigenvectors. Let's take a look at another example here. So let's see, and now we'll take a look at a 3 by 3 example. And let's find the eigenvalues. This is going to be a bit more involved. So a minus lambda I. I'm going to subtract lambda on the main diagonal. So 2 minus lambda. And then in the middle, 3 minus lambda. And then bottom corner, 2 minus lambda. But all the rest of those entries are going to stay the same. And I want to find the determinant of a minus lambda I. Now, since nothing really looks advantageous here, and I'm going to say, don't start doing row operations. Don't do that. Because I have an issue then where I'm going to be moving this sort of term lambda around. It's going to make things a very, very, very big mess. Don't do it. It's not worth it. I'm going to say it again. Don't do row replacement or anything like that. Just go for a good old-fashioned cofactor expansion. Don't do anything. Cofactor expansion. And since everything looks just about as bad as everything else, I'm just going to do a classic cofactor expansion across the top row. I'm going to pick out the 2 minus lambda times the determinant of the 2 by 2 matrix when I remove that entries row and column. So that's 3 minus lambda, negative 1, negative 2, 2 minus lambda. I got to bring out the 2, but I got to flip its sign. So negative 2 times the determinant of the 2 by 2 matrix when I remove that entries row and column. So that's 1, negative 1, negative 1, and then 2 minus lambda. And then I got to bring out negative 1, and I don't flip its sign, so it stays negative 1 times the determinant of the 2 by 2 matrix that I get when I remove that entries row and column. And that's going to give me 1, 3 minus lambda, negative 1, negative 2. And let's keep going with this. So here I have 2 minus lambda times, here in my brackets, I'm going to have 3 minus lambda times 2 minus lambda. And then minus negative 1 times negative 2 just gives me 2. Here I have negative 2 times this determinant, 1 times 2 minus lambda is 2 minus lambda. And then minus negative 1 times negative 1 is 1. And then minus 1 times, here I can find this determinant, 1 times negative 2 is negative 2. And then minus negative 1 times 3 minus lambda. So let's think about this. I'm subtracting it, and it's the product of negative 1 and something else. So that minus, the subtraction, and then this negative 1 are just going to like simplify, resolve. So I'm going to get plus 3 minus lambda. You can do the work to check that if you don't believe me, but I think you do. Now let's see where we go from here. So I'm going to leave this written the way it is for now. That's 2 minus lambda. I'll come back for it though. Then in the brackets here, I have this 3 minus lambda times 2 minus lambda, and then minus 2. And then here, let me expand this stuff out. So here, let me distribute. Let me try to put everything in descending order too. I have negative 2 times negative lambda is going to give me plus 2 lambda. 2 minus 1 gives me 1 times negative 2 gives me negative 2. And then here, negative 1 times negative lambda gives me plus lambda. 3 minus 2 gives me 1 times negative 1 gives me minus 1. And then let me keep going here. So I'm going to leave this as it is. Sometimes expanding things out isn't always the best thing to do. Maybe I'll end up doing it anyways, but let me at least make sure it's the decision that I want for my life. So here, if I take a look at what I have, 2 lambda plus lambda gives me 3 lambda. Negative 2 minus 1 gives me negative 3. So it looks like nothing really apparent jumps out. So I would say let's go ahead and expand inside the brackets here. 2 minus lambda, and then in my brackets, negative lambda times negative lambda gives me positive lambda squared. I have negative 2 lambda, and minus 3 lambda is going to give me negative 5 lambda. 3 times 2 is going to give me 6, but don't forget about this minus 2 here. 6 minus 2 gives me plus 4. And then I have this plus 3 lambda minus 3, and I'm going to factor a 3 out. Leaves a lambda minus 1 behind. Now, this inside the brackets I can factor, so I'm not going to expand this further. I don't think that's wise. But here, I can write this lambda squared minus 5 lambda plus 4 as a product of 2 binomials. And if it multiplies to 4 but adds to negative 5, it's going to be minus 4 and minus 1. And here I have this 3 times lambda minus 1. Now this is something that I can factor again, and I'll show you why. Because here, think of this like one term plus another term, but in the first term I have a factor lambda minus 1, and in the second term I have a factor of lambda minus 1. So if I was going to factor that all the way out, it would be lambda minus 1 in parentheses times, and then I have this 2 minus lambda times lambda minus 4 and then plus 3. Let me actually close it there because it looks like I misjudged the amount of free space I had. And then from here, what I can do is I can go ahead and now expand inside. Hoping this gives me something that looks nice at some point. But let's see. So here I have lambda minus 1. And inside the brackets, negative lambda times lambda gives me negative lambda squared. I'm going to have negative lambda times negative 4 gives me plus 4 lambda. I'm going to have 2 times lambda gives me plus 2 lambda. And have 2 times negative 4 gives me negative 8, and then plus 3 is still hanging out. Okay, let's keep going. Keep going. Lambda minus 1 in front. Leave me a comment below if you're having a good time right now. We have minus lambda squared. We'll do plus 6 lambda, and then minus 5. And just for the sake of convenience, I'm going to factor a negative 1 out. So I'm going to say I have lambda minus 1. I'm going to factor a negative 1 out of my trinomial, and that's going to flip the sign on everything inside. Lambda squared minus 6 lambda plus 5. And let's see if we can't factor this. We're in it to win it. I think we're almost there. Lambda minus 1 times negative 1. Can I factor this? Lambda and lambda multiplies to positive 5 and adds to a negative 6. Okay, I'm thinking it's going to be lambda minus 1 minus 5. Negative 1 times negative 5 is positive 5. Negative 1 lambda minus 5 lambda is negative 6 lambda. This is my determinant. Fully factored. I can set it equal to 0. What are my eigenvalues? I get lambda equals 1. This is a throwaway term. You can divide it away. I get another lambda equals 1. And then I get lambda equals 5. These are my eigenvalues. Or we could say lambda equals 1 with multiplicity 2. If you want to list it out twice, though, that's fine. Don't list it once, and don't mention the multiplicity, though. That would be bad. But these are my eigenvalues. 1, 1, 5. Hey, we did it. There's still a lot more work to do, though, so don't get comfortable. If you have a soft drink that you're drinking, or if you're drinking coffee, let me know. But now I want to work with these eigenvalues. Let me start with lambda equals 5. And I want to plug this in, and I want to augment with the 0 vector. So with lambda equals 5, if I subtract 5, 2 minus 5 is going to give me negative 3. And then we had 2 and negative 1. And then 3 minus 5 is going to give me -2. So 1, -2, -1. And then 2 minus 5 is going to give me -3. So -1, -2, -3. So this is what it looks like when I plug in the eigenvalue of 5. And let me do a row interchange on the rows 1 and 2, because I want this 1 in the upper left corner. So 1, -2, -1, augmented with 0. My second row is going to be -3, 2, -1, augmented with 0. And I'll leave that bottom row as it is, -1, -2, -3, augmented with 0. Looks good. Looks good. Now let me use that 1 in the upper left corner to do some row reduction. So I'm going to replace row 2 with row 2 plus 3 times row 1. I'm going to replace row 3 with row 3 plus row 1. Row 1, I'm just going to rewrite it. Row 2's position, -3 plus 3 times 1 gives me the 0 that I wanted. 2 plus 3 times -2, that's going to give me 2 plus -6 is going to give me -4. And -1 plus 3 times -1, that's -1 plus -3 gives me -4. Then augmented with 0 plus 3 times 0 gives me 0. And in row 3's position, I get -1 plus 1 gives me the 0 that I wanted. -2 plus -2 gives me -4. -3 plus -1 gives me -4. And then augmented with 0 plus 0 gives me 0. Now I can see that rows 2 and 3 are identical, so I can go ahead and scale them and then remove one of them. We'll do a -1/4 row 2, a -1/4 row 3. So I'll rewrite row 1. And then rows 2 and 3 are both going to become 0, 1, 1, augmented with 0. I can do some row replacement. So I can replace row 3 with row 3 minus row 2. And I can replace row 1 with row 1 plus 2 times row 2 to give me that 0 that I'm going to need. So I'll rewrite row 2 to start, 0, 1, 1, augmented with 0. Row 3 is going to become that perfect row of zeros at the bottom. But then here I'm trying to get this 0 in the second entry of row 1. So I'm going to get 1 plus 2 times 0 keeps my 1. -2 plus 2 times 1 gives me that 0 that I wanted. -1 plus 2 times 1 is going to give me -1 plus 2 gives me +1. And then augmented with 0 plus 2 times 0. Now this is fully reduced, right? And what are the remaining rows trying to tell me? The first row says v1 plus v3 equals 0. Second row says v2 plus v3 equals 0. So then in this case, we could say, okay, so then v1 equals -v3, v2 equals -v3, and I want to pick my vector. So my vector v has entries v1, v2, v3 in it. And picking this vector, I want it to look as nice as possible. That's always my goal. Get a nice looking vector. I'm going to pick v3 to be -1. And v1 and v2 are just the opposite of this, so those are both going to be +1. Now you could pick the vector -1, -1, +1. I think that's reasonable. I wouldn't think that's the end of the world. That would be fine. But I think the vector 1, 1, -1 looks a little bit nicer, but you know. This is my eigenvector. And this eigenvector corresponds to an eigenvalue of 5. So far so good, but I got some more work to do because I had the other eigenvalue of 1, and that was repeated. So right away, we know that there could be an issue. I want this to be diagonalizable. Since I only have one more eigenvalue, and my matrix is a 3 by 3, which means I need 3 eigenvectors in total. I already have one eigenvector. It means I need 2. I need 2 eigenvectors from this one eigenvalue. Hopefully, it doesn't mess me up. You better give me all the eigenvectors I'm looking for. I need you to do 2. I need you to do 2 eigenvectors. Let's see. Let's set this up. Hopefully successful. So now I'm going to be subtracting lambda off the main diagonal. Lambda is 1 this time. So 2 minus 1 gives me 1, so I'm going to get 1, 2, negative 1. Lambda equals 1, so right in the middle, I'm going to get 3 minus 1 is 2, so 1, 2, negative 1 again. And lambda equals 1, right? So here at the very end, 2 minus 1 is going to give me 1, so negative 1, negative 2, 1. Negative 1, negative 2, 1. Now, this looks like a fun one to reduce. I can replace row 2 with row 2 minus row 1. And I can replace row 3 with row 3 plus row 1. So I'll rewrite row 1 to start. 1, 2, negative 1, and then augmented with 0. But since row 2 and row 1s are identical, when I subtract one from the other, it just gives me that row of all zeros. And row 3 is not really different, it's just scaled through by a negative 1, so when I do row 3 plus row 1 in row 3's position, gives me another row of all zeros. And this is actually fully reduced. And the remaining row, the remaining non-trivial row, tells me v1 plus 2v2 minus v3 equals 0. And if I solve for v1, we get v1 is negative 2v2 plus v3. Remember we were saying you could start by building this in like a parametric vector form. That's fine. So say vector v, it's going to be some numerical vector times free variable v2 plus some numerical vector times free variable v3. We'll say v1 is 2v2 minus 1v3, and then v2 is free variable, so 1 and 0, and v3 is free variable, so 0 and 1. Oh, sorry, I'm looking here. Whoops. That was my mistake on those top entries. Don't judge me. If you want to judge me, you can judge me in the comment section below. I was looking here. I should be looking here. Yes. Let's do this again. v1 is a negative 2 times v2 plus 1 times v3. Okay, I feel better. Thank you. So looking at this, I can actually see my eigenvectors if I want to just use these ones. You know that I like that first entry to be positive, arbitrarily because of the way I was raised. So I would probably do something like this. I would say, well, let me let v2 be a negative 1, flipping the sign. Let v3 be 1. I'm not trying to combine these into one vector, though. Really, I'm looking at these as vectors to build a basis. And we're saying that any scalar multiple that is a non-trivial vector still will be fine for an eigenvector. So you could pick for an eigenvector negative 2, 1, 0. Or if you want to flip the signs on it, you could pick for an eigenvector positive 2, negative 1, 0 is fine still. Right? These are not really that dissimilar. They're going to be multiples of each other. And you could pick here, you could pick negative 1, 0, negative 1. You could pick negative 9, 0, negative 9. But I actually like the way this vector looks already. So 1, 0, 1 looks good. And that's going to be my other eigenvector. And this builds a basis for the eigenspace corresponding to lambda equals 1. Now we can build these wonderful matrices P and D. So matrix P, a 3 by 3 matrix. Diagonal matrix D, also a 3 by 3 matrix. And I know how that diagonal matrix is going to look. I'm going to have on the diagonal those entries from the eigenvalues, but everything else has to be a 0. Now I'm going to do these in order. So I had eigenvalues 5, 1, and 1 that I worked with. I only worked with the eigenvalue 1 once over, but it did give me 2 vectors. As soon as I place the diagonal entries of D, I've already determined how these vectors of P are going to look, the column vectors. So in this first column of D, the diagonal entry is eigenvalue 5. This first column of P better correspond to eigenvalue 5's eigenvector. What was that vector? It's right here. It was 1, 1, negative 1. And we said, well, you could have something like negative 1, positive 1. That's still fine. Nothing to worry about. Next, though, in the last two columns should be the eigenvectors that correspond to the eigenvalue 1. Since there are two of them, you could sort of have some freedom here, but put one column and put the other in the other column. I'm just going to do them in order anyways. Column 2, -1, 0, column 1, 0, 1. You could interchange these two columns and it still doesn't really matter because interchanging these two diagonal entries has no significance, right? But these are the matrices P and D that do the diagonalizing, which is how we would present our answer. Looks really good. Very pleased with how that worked out. We got it. Take a look at one more example diagonalizing. Diagonalize the given matrix. I want to find the eigenvalues, but notice this is a triangular matrix. It is lower triangular, since I have this sort of upper pizza slice, pepperoni pizza. So triangular matrix. The eigenvalues are 2, 2, 2. The entries on the main diagonal. So lambda equals 2, lambda equals 2, lambda equals 2. Or you could say lambda equals 2 with multiplicity 3, since it appears 3 times over. Now I'm not going to work with this 3 times. I only want to work with it once because it's not going to give me any new information. But I'm hoping that this will give me 3 linearly independent eigenvectors, or else it's not going to work. Let's see. If I work with lambda equals 2, subtracting 2 on the main diagonal, 2 minus 2 gives me 0, and then again, and then again, and all the rest of the entries stay the same. This is the matrix that I get for A minus lambda I. And I want to augment this with the 0 vector. So let me actually augment this. Kind of a lazy augmentation, but I did it. Now I'm going to do some row swap. I'm going to put row 2 at the top. I'm going to put row 1 at the bottom and row 3 right in the middle. So my top row is going to be 2, 0, 0 augmented with 0. My middle row is going to be 2, 2, 0 augmented with 0. And my row of all zeros should be at the bottom. And then from here, I can scale rows 1 and 2. So 1/2 row 1, 1/2 row 2. It's going to give me 1, 0, 0 augmented with 0, 1, 1, 0 augmented with 0, and then my row of all zeros at the bottom. And this is almost fully reduced. I would want to replace row 2 with row 2 minus row 1. So I can rewrite row 1. And then row 2, 1 minus 1 gives me 0, 1 minus 0 gives me 1, 0 minus 0 gives me 0, and then again. And then row 3 is going to stay as that row of all zeros. Now what is this telling me? Well, the first row says v1 equals 0. Second row says v2 equals 0. And then v3 is my free variable, so v3 is itself. So when I go to build this vector, not actually too difficult to do. I know that v1 is 0, the first entry is 0. The second entry, v2, must be 0. The third entry can be whatever I choose it to be. I need to make sure this is a non-trivial vector though, so don't pick 0. Don't pick 0. What are you going to pick? I know what you should pick. You better pick 1. Just make it easy on everybody. So this is the vector that I get from the eigenvalue 2. There's a problem though, right? How many vectors did I need? I needed 3 vectors. This gave me 1 vector. I'm short by 2 vectors, so there's no way that I can diagonalize here. So I'm not going to be able to do this. So we can make a comment. We need 3 linearly independent eigenvectors to diagonalize a 3 by 3 matrix. I only have 1 eigenvector. So matrix A is not diagonalizable. We'll say is not a diagonalizable matrix. Remember, not all matrices can be diagonalized. I need to make sure that I have enough eigenvectors. Just a few theorems to end with here, which hopefully come full circle for us. An n by n matrix with n distinct eigenvalues is diagonalizable. And let's sort of talk about why this is. We noticed that the issues that we ran into are when we had some eigenvalue of multiplicity other than 1. If I have an eigenvalue, let's say, of multiplicity k, I need that eigenvalue to give me exactly k eigenvectors. So if I have an eigenvalue of multiplicity 2, it better give me 2 eigenvectors. If I have an eigenvalue of multiplicity 3, like we just ended with, it better give me 3 eigenvectors. However, if all of my eigenvalues are different, so they all have multiplicity 1 and I've got n of them, then every single one of those eigenvalues is going to produce a non-trivial eigenvector. So really the only concern we would have with diagonalizing is if I have some eigenvalue of multiplicity other than 1. Right? With some multiplicity, then we'd say, well, now I'm nervous because either it's going to give me enough eigenvectors and whew, everything's okay now, or it's not going to give me enough eigenvectors, and that's going to be a big issue. However, if all of my eigenvalues are different numbers, all of multiplicity 1, then I know that each one of those eigenvalues is going to produce an eigenvector, and everything's going to work out really well. So that's a good sign if I have distinct eigenvalues for all of my eigenvalues. Then I know, hey, it's going to work, right? It's that multiplicity that makes me nervous, because that could work, but also could not work. A nice theorem here. Let A be an n by n matrix with distinct eigenvalues, lambda sub 1, lambda sub 2, so on and so forth, to lambda sub p. For 1 less than or equal to k less than or equal to p, the dimension of the eigenspace for lambda sub k is less than or equal to the multiplicity of the eigenvalue lambda sub k. So this is basically saying that if I'm finding eigenvectors and then finding the dimension of the eigenspace, the dimension is either going to be less than or the same as the multiplicity of the eigenvalue that I'm doing it for. And if it's equal to, then that's good. We got enough eigenvectors out of that eigenvalue, but it could also be less than. It's not going to be more than, though. I'm not going to get too many vectors, right? That has to do with the multiplicity. Second, the matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspaces equals n. And this happens if and only if the following two. The characteristic polynomial factors completely into linear factors, and the dimension of the eigenspace for each lambda sub k is in fact equal to the multiplicity of lambda sub k. So essentially saying, I need to make sure I have enough eigenvectors. If you are an eigenvalue of multiplicity 7, then you better give me 7 eigenvectors, and your eigenspace better be 7-dimensional, or else you're not doing enough. You're not giving me enough to work with, like that, etc. And then lastly, if A is diagonalizable and beta sub k is a basis for the eigenspace corresponding to eigenvalue lambda sub k for each k, then the total collection of these vectors in the sets forms an eigenvector basis for the vector space Rn. If I have enough of these linearly independent vectors, it will build me a complete basis out of eigenvectors. We call that an eigenvector basis. Hey, I hope you enjoyed this lecture. I love talking about diagonalization. We're going to talk more about this in the course. It's not going to go away. But no matter where you are and what you're doing, I hope that you will always keep learning, keep dreaming, and follow your heart. We'll be back at it with more math and more cat stuff soon. But until then, I will see you later. See you next time. So stay close by.